Here's another example. Instead of being given characteristics of a graph and not knowing the equation, here we're given the equation of a graph. And we need to do the same thing, find the intervals of increase and decrease, the max and mins, concavity, and sketch it. To find the intervals of increase and decrease, we take the first derivative and we find where it's greater than 0 and less than 0. And while we're doing that, we're finding the critical values, so we can find the max and mins with the first derivative test while we're finding where it's increasing and decreasing. So I take the derivative of this, and its expression, and then to see where that is greater than 0, it's going to tell me the interval where f is increasing. So remember, to solve an inequality, you want to set it relative to 0. You set it as an equation. And then I'm going to factor. I'm going to treat this as a difference of two squares. And I'm going to factor. And then I'm going to set each factor equal to 0. So this factor tells me that x equals 0 and x equals minus 2 are critical values. That's when this factor is 0. And this factor is never 0. These are my two critical values. And I'm going to test the first derivative around these values to see what it's doing. So f prime's greater than 0, to the left of minus 2, and to the right of 0. And f prime's less than 0 between minus 2 and 0. So it's increasing on this interval, and it's decreasing on this interval. We know f has a local maximum at minus 2. So when I evaluate the original function of that, I got the value of y equals 7. And then it had a local minimum at x equals 0, and that gives me minus 1. So now to find the intervals of concavity and the inflection points, I want to find that second derivative and set that equal to 0. Well, the second derivative is this cubic. And the only place that is 0 is when x is minus 1. And to the left of minus 1 is where the second derivative is less than 0. And to the right of minus 1 is where it's greater than 0. Therefore, minus 1, when I plug minus 1 into my original equation, minus 1, 3 is an inflection point. And it's concave down to the left of minus 1 and concave up to the right of minus 1. So to sketch that, you want to plot a few points besides just the max and min and the inflection point. So I plotted another point here at x equals 1 and at x equals minus 3. And then remember from pre-calc days, this is a polynomial. It's of degree 5. So remember what the end behavior does. So it's going to go to negative infinity for x as x goes to negative infinity, and it's going to go to positive infinity as x goes to positive infinity. So that's the end behavior of an odd degree polynomial. So you sketch that first and then kind of fill it in. So I know that it's going to go up to this local max, come through this inflection point, come down to this local min, and then connect up here again. And I'm going to try to make it change concavity at this inflection point. And instead of my horrific drawing, I let Desmos fill it in. So notice that this inflection point, the change in concavity looks very subtle here. So that's why I'm saying that doing it by hand, if it's subtle, it can be pretty tricky. So you want to mark it, inflection point. Example 6. Now you're asked to find the vertical and horizontal asymptotes in addition to all the other stuff. So remember to find the asymptotes. This doesn't have any vertical asymptotes. But to find the horizontal asymptote, we'll find the limit at infinity. And you brush off those skills. So as x goes to infinity, we can multiply by the conjugate over the conjugate. And we see that this goes to 0. So we have a horizontal asymptote at y equals 0. to find the intervals of increase and decrease in the local max and mins, I'm going to find the first derivative. And so notice the first derivative is less than 0 everywhere. And the reason that is because this term is less than 1 everywhere. And that's because notice that I have x squared plus 1 in this square root in the denominator. So this is always going to be larger than x. So this whole expression will be less than 1. So that's going to be less than 0 everywhere, which tells me my function is going to be decreasing to the left and right of 0. Also, since f prime is less than 0 everywhere, it can't equal 0 anywhere, which means that we don't have any local extrema. And then we're supposed to find the intervals of concavity. And unfortunately, this is falling off the end of the screen here. But if you find the second derivative, again, you're going to find it evaluates to this. And that's greater than 0 for all x, because x, no matter what x is, when I square it, it's positive. And then this is always going to be positive. So this graph is concave up everywhere. And again, since the second derivative is never equal to 0, there are no inflection points. So then to do this, to plot this, to sketch it by hand, you want to plot a few random points from the original function. You know that it has a horizontal asymptote at the y-axis. You know that it's concave up everywhere. It's not turning around. It doesn't have any local max or mins. So if you plot several points on it, then it's you can just fairly straightforward to connect them and have the graph skim along the x-axis. This was a big, huge section, and there are a lot of problems in the homework. But summarizing, the first derivative tells us where a function's increasing or decreasing, and it will tell us where it has a maximum or a minimum, local max or min. The second derivative tells us where a function's concave up or concave down, and where it changes concavity is the inflection point, and that's where the second derivative is 0.